Okay, so I was asked to review the method that we used in class for finding this derivative. So the first thing that I did is I rewrote the function as a product. So I made this x times x squared plus 2 to the negative 1/2 power. Now, hopefully by the end of this video, you're going to see sometimes this method's easier, sometimes just using the quotient rule is easier. I'm going to use the quotient rule with this example and then sort of let you decide which one you want to do. Okay, so derivative, first function times the derivative of the second function. Using the chain rule, I have to multiply by the derivative of the inside, plus second function times the derivative of the first function. Okay, so I think we're pretty solid with product and quotient because we've been using it so much. But now from here, to simplify it, if you were just to write these as two different terms, you have exactly that, two different terms. So the goal is to be able to get the derivative as one rational expression. So from here, I'm really just using what we've already learned about factoring with the GCF. So if I gave you this polynomial and I asked you to factor it, you know, because it's so common that you use it, that I have to look for the greatest number I can take out of both terms. Okay, well, that greatest number I can take out of both terms is an x squared. Once we determine what the GCF was, then we, without writing this step necessarily, we divide that out. This simplifies to x squared. X squared divided by x squared gives me 1. So I'm using that exact same method here. But now my method is just dealing with negative exponents. So when I look at my GCF, which is, I think we can easily agree on, x squared plus 2, what is the smaller of those two exponents? A negative 3/2. I'm going to bring this down so I can show the divide step. What am I left with? Okay, these two cancel, and I'm left with the negative x squared here. Because when I divide by the GCF, it'll always just cancel out of one term. Okay. And then when I divide by x squared plus 2 to the negative 3/2, all right, these are like bases. Okay, so remember our rule, our exponent rule, when we divide like bases, we subtract exponents. So negative 1/2 minus negative 3/2. Okay, and this is really the step that trips up a lot of students, because you got to understand that that'll always just go to the first power. Okay, so what am I left with here? I'm really just left with x squared plus 2 to the first power. Now I'm writing it in parentheses just to show the step completely. Okay, then I'm left with negative x squared plus 2. All right, those guys cancel, so I'm just left with 2 over x squared plus 2 to the 3/2 power. So there's my derivative. So once you get comfortable with understanding that it's really just factoring by GCF, I don't think it's a difficult method. Okay, let's look at the derivative using the quotient rule. So bottom, actually write this as 1/2. Bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. Okay, so when we look at this, 1, 2, now we're really dealing with 3 terms, okay, 3 pieces of this rational expression. So you still need to be able to simplify it and verify that we get that 2 over x squared plus 2 to the 3/2. Several different things you can do here. Okay, one method, I can look at this. I can make my exponent positive there. All right, so, and I'm not going to proceed with this, but you can get a GCF in the numerator. Then you can take that numerator and multiply it by the reciprocal of the denominator and still simplify from there. Okay, so that's like technically one method you could proceed with. Okay, another method that you could proceed with, and someone had done this in class, I could take each term of my numerator, divide it by my denominator. Okay. Right, because that x squared plus 2 on the bottom is really being raised to the first power. All right, here I am. I'm dividing like bases, dividing like bases. I'm going to subtract my exponents. Negative half minus 1 gives me a negative 3 halves. Negative half, oh, oops, this should be positive half. Sorry about that. 1 half minus 1 gives me a negative 1 half. Negative 1 half minus 1 gives me a negative 3 halves. Okay, so from this method, you still got to understand though, I still have two terms that have a negative exponent, right? So I really have to be able to factor out that GCF again. So this method would still use the fact that negative 3 halves is common to both of them, and then what are you left with? All right, we already proved what we would be left with, which would be x squared plus 2 minus x squared. So not too much, but that'll get us the answer pretty quickly. Or the third step, it really includes that GCF again. So if I look at my numerator, in my numerator, x squared plus 2 to the negative 1 half is common to both parts of the numerator. 1 half. So if I factor out, right, if I divide by x squared plus 2 to the negative half power out of both of these, right, and this is only for method 3, then 1 half minus negative 1 half gives me 1. So I got my x squared plus 2 to the first. In the second term, they completely cancel, so I get to get rid of my negative x squared. But I still, don't forget, I still have that x squared plus 2 to the first power in the bottom. So when a quotient rule involves a rational exponent, I don't think that the quotient rule is the easiest method. So when a function, if I were to rewrite it as a product rule, involves a rational exponent, I think it's easy. Because there's 1, 2, basically 3 steps and I'm done the derivative. Now, when we look at the derivative as 2 over x squared plus 2 to the 3 halves power, now for the second derivative, that should be really easy because I don't even need quotient, right? I don't have an x in the numerator. So I would definitely tell you to rewrite it as a product rule because now when I look at that, it's just chain. So 2, bring the exponent down front, subtract 1 from the exponent, multiply by the derivative of the inside. So I got these to cancel. I have a negative 6x over x squared plus 2 to the 5 halves. So you really gotta, part of finding derivatives is understanding which method works when. Okay, so I definitely think that's the harder of the two that we did. So now let me go to this one, where it's the exact same except for that square root on the bottom. All right, so in class, I wrote it as a product. So first derivative. First times the derivative of the second plus second times the derivative of the first. Okay? So like the method we just used, my GCF here would be x squared plus 2 to the negative 2. Okay. Factoring that out of each term, So I'd be left with negative 2x squared. And then this negative 1 minus negative 2, this would give me plus x squared plus 2. So I get negative x squared plus 2 in the numerator, all over x squared plus 2 quantity squared. So not difficult. I mean, especially because the exponents are integers, I think they're a lot easier to make sense in your head. Okay, still 1, 2, 3 steps and we're done. Okay, but now let's look at the quotient rule for this one. So if I were to look at the derivative as bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. Now it's just a very simple combining of like terms. And we get the exact same answer. Okay, so like on this example, quotient rule is great. Why is quotient rule great? Because when I derive using the chain rule on the bottom, I don't have any I don't have any fractions. I don't have any negative exponents, right? Like those things work really nicely. So again, you have to be able to determine what works best for you. Now let's look at the second derivative. Okay, so in class, pretty sure I wrote it as a, okay, yeah, so first derivative, I kept it as a product. Just want to see what I did in class. First times the derivative of the second. Don't forget our chain rule. Plus second times the derivative of the first. All right, use my GCF bit again. So x squared plus 2 to the negative third. So that leaves me with negative 2 times 2x. That gives me a negative 4x times this negative x squared plus 2. So you do have to be careful that that'll take some distributing. Dividing by x squared plus 2 to the negative third. Negative 2 plus 3 gives me 1. So that'll be minus 2x times x squared plus 2 to the first. Okay, so I get 4x cubed minus 8x minus 2x cubed minus 4x. So combining and making this exponent positive, I get 2x cubed minus 12x all over x squared plus 2 cubed. Okay, so if we're sort of in the zone of using that GCF factoring technique with negative exponents, that sort of works. But I only have a minute left, so I'm not going to be able to do it. But I encourage you to use the quotient rule to find f double prime and tell yourself which one works better. Okay, so use the quotient rule knowing that this is the first derivative, and then prove to yourself what, if you were taking a test, you think you would use. Okay, I hope you found this helpful.